Okay, let's dive into this. Picture this. A quiet desert morning, New Mexico. July 16th, 1945. There's this stark tower against the sky,
Hmm.
and then just this flash, this incredible roar, an almost, well, unbelievable burst of energy.
The start of the atomic age, right? The Trinity test.
It really was.
Yeah.
And that wasn't just, a test in the usual sense. It fundamentally changed the actual ground it happened on.
The power involved. I mean, temperatures over 8,000 Kelvin. For a moment, hotter than the sun.
Exactly. And that kind of energy doesn't just, well, destroy things. It actually created something, too.
Created something new from the old stuff that was there.
Yeah. As all that energy expanded outwards, it just scooped up the desert sand, the steel tower, instruments, everything at ground zero.
Vaporized it.
Vaporized it, melted it, and then as things cooled down incredibly fast, those materials fused together, formed a completely new substance.
And that is Trinitite. That's Trinitite. It's this glassy, usually kind of greenish material they found coating the test site afterwards. A real tangible piece of that first atomic explosion, like a man-made rock born from these really extreme forces.
And that's exactly what we're digging into today. You've shared some fascinating sources with us, scientific papers, detailed analyses, all about this unique stuff. So our mission, in this deep dive is to explore the science behind it, how it formed, and why it's actually pretty significant, all based on what these materials tell us.
Absolutely. We need to look at how those just extreme conditions shaped this glass. We'll get into its really complex internal structure and what it's made of.
And why scientists are still studying it decades later.
Yeah, because it offers insights into everything from fundamental physics to, believe it or not, nuclear forensics.
And you hinted before, there are secrets buried in that glass we're still figuring out.
Right.
Actual bits of the bomb.
Yeah.
And even a form of matter.
Yeah.
Well, something really unexpected.
That's right.
Okay, so let's start right at the beginning. The fiery birth of this stuff.
Okay, so Trinity test. July 1645, New Mexico, like you said. It was a plutonium implosion bomb. Pretty similar in design, actually, to the one used later on Nagasaki.
And the power. I read recent estimates put it higher than they first thought.
Yeah, the research you sent over suggests the yield was actually quite a bit higher, maybe around 24.8 kilotons of TNT equivalent. Older estimates were lower.
Wow. That much energy hitting the ground. It's hard to really grasp the scale of, well, destruction and creation happening all at once.
It really is. That intense heat, the pressure, it vaporized steel, copper wires, and of course the desert sand itself. All this material got swept up into the fireball, the mushroom cloud.
So the Trinitite formed when all that vaporized stuff cooled down and fell back to Earth, like atomic rain.
That seems to be one of the main ways, yeah. The studies describe how material in that hot vapor cloud condensed into tiny droplets. These droplets bumped into each other, stuck together, agglomerated, and then rained down onto the surface.
Where they cooled really fast.
Exactly. Quenched is the term they use. Rapid cooling on the ground.
But I think the sources mentioned another process too, something about melting happening right on the ground.
Yes, that's the other key scenario. The intense heat radiating from the fireball, even before the blast wave maybe, was enough to melt the desert surface in situ right where it sat. Then this molten layer got quenched, cooled, possibly by the rush of air coming back in towards the blast center after the initial expansion.
So both things happened, rain down and surface melting.
The sources suggest both were happening, yeah. Maybe in slightly different places or contributing in different ways. That helps explain why Trinitite samples can look different, have different textures, sometimes even layers. It wasn't just one simple event.
Right, that makes sense. Something born from such a messy, violent event would likely be complex itself. And you mentioned some of the shapes it formed look a bit like things found in nature.
They do, which is fascinating. The way some molten droplets got carried up, swirled around in the atmosphere, and cooled quickly, they formed these little beads, sometimes dumbbell shapes.
Like tiny glass weights.
Sort of, yeah. And the research points out how similar these look morphologically to tektites.
Tektites, those are the glassy bits from meteorite impacts, right?
Exactly. Natural glasses formed by cosmic impacts. And other features in Trinitite, some of the textures, are compared to fulgurites.
Fulgurites, what are they?
Those are the glassy tubes or crusts you get when lightning strikes sand or rock. It melts the material along its path.
Wow. So nuclear blast, meteorite impact, lightning strike, these incredibly high-energy, rapid cooling events can all end up making similar kinds of glassy materials.
It seems so. It really puts the energy involved in the Trinity test into a kind of geological perspective, doesn't it?
It absolutely does.
Yeah.
Okay, let's zoom in a bit. If you actually pick up a piece of Trinitite, what are you looking at? What's inside, its structure, its composition?
Well, the original sand there, it was what geologists call arcosic sand. Lots of quartz, but also feldspars minerals like microcline and albite, some mica, actinolite, talcite, typical desert stuff.
Yep.
But when the blast hit, something interesting happened. Only the quartz grains, which have a very high melting point, managed to stay mostly crystalline, though even they often show signs of melting around the edges.
And everything else, the feldspars, the mica.
All melted, completely.
So you end up with this glassy matrix, this sort of background material with bits of partially melted quartz kind of floating in it.
That's a good way to put it. And the glass itself, if you look under a microscope, it's incredibly complex. It's really heterogeneous, meaning it varies a lot over tiny distances, like tens or hundreds of micrometers.
So not uniform at all.
Not really. You see different glassy phases mixed together. Some patches are rich in, say, calcium, magnesium, and iron. Others are rich in alkalis like potassium and sodium from the feldspars. And then there are areas that are almost pure silica glass.
Why so much variation?
It reflects the fact that the original mineral grains didn't perfectly mix together when they melted in that incredibly short time. It's like a snapshot of incomplete melting and mixing.
And what about the bubbles? I always picture Trinitite as being kind of bubbly or frothy.
You're right. Vesicles, microbubbles are very characteristic. And their size and how they're distributed tell us a lot about the cooling history, too.
How so?
Well, the sources note that the very top glassy layer often has fewer bubbles, but the ones it does have are bigger and rounder, go deeper into the sample into the lower zones, and you tend to find more bubbles, but they're smaller.
Interesting. So fewer, bigger bubbles on top, more smaller ones below.
Generally, yes, and their shape is also a clue.
Cheap.
Often, especially near the top, the bubbles are elongated, kind of stretched out parallel to the original ground surface.
What does that mean?
That elongation strongly suggests very rapid cooling, quenching of that top surface, stretching the bubbles as the glass solidified. The material underneath may be insulated a bit, likely stayed hotter for slightly longer.
Allowing more gas to come out and form those denser, smaller bubbles.
That's the interpretation, yeah. Prolonged heating below. It's also noted that areas rich in potassium, probably from melted K-feldspar, often have more bubbles. Perhaps those grains degassed more as they melted.
So even the tiny bubbles are like little records of the heat flow and mineral reactions.
Yeah, exactly. It's like reading a very fast, very violent geological event in micro detail.
Amazing. Okay, visually, we usually think of Trinitite as green, right?
Mm-hmm.
Is that always the case?
Green is definitely the most common color, yeah. That typical greenish tinge. But there's another famous type, red Trinitite.
Red? Where does the red come from?
That color comes from copper. The analysis traced it back to the copper wires that were part of the test setup connecting the bomb to the diagnostic instruments and firing circuits. They got vaporized, too.
So the color itself tells you something about what specific materials got caught up in the blast.
Precisely. And besides the green and the red, you find different forms, too. There's something called pancake Trinitite, basically a glassy crust on top of these sort of solidified blobs.
Right.
There are also scoriaceous fragments. These are really glassy and full of holes, very vesicular, looking a bit like volcanic scoria. And then, like we mentioned, those little beads and dumbbells that formed from airborne droplets cooling down.
This is quite a variety. But the sources you shared mentioned something even more, well, mind-blowing, found inside some pieces, especially the red Trinitite. Tiny metallic bits.
Ah, yes, the metallic inclusions. This is where it gets really fascinating from a forensic perspective. Scientists looking closely at red Trinitite found these tiny metallic chondrules, small, spherical, or rounded particles embedded right in the glass.
Chondrules, like in meteorites. But these aren't natural.
No, not in this context. Analysis confirms these are melted bits of the bomb itself and the steel tower it was sitting on.
You mean actual fragments of the device fused into the glass?
That's exactly what the research shows. They use techniques like scanning electron microscopy, SCM, often combined with an X-ray detector, to map out the elements in these tiny specks.
What did they find?
The sources mention finding elements like iron, copper, and lead. And the images show incredible detail, like seeing where molten iron and molten copper separated out because they don't mix well, like oil and water.
Immiscible liquids, yeah.
Right. And they could even see that lead was mostly found within the copper areas. This level of detail basically confirms these are remnants of the bomb's components, the casing, the wiring, maybe even tamper materials, history literally encased in glass.
Wow. A microscopic artifact of the bomb itself. And speaking of incredible microscopic structures, this brings us to perhaps the most surprising discovery of all from Trinitite, something really fundamental.
Ah, you mean the quasi-crystal.
Yes, a quasi-crystal. I mean, what is that exactly? The name itself sounds almost like a contradiction. Ordered, but not repeating.
It's a really unusual form of solid matter. So you know how in a normal crystal, atoms are arranged in a pattern that repeats perfectly over and over again, like tiles on a floor?
Right.
A quasi-crystal also has an ordered structure. The atoms aren't just randomly placed, but the pattern never repeats itself periodically. Think of maybe those Penrose tilings. You can cover a whole surface with specific shapes according to rules, but the overall pattern doesn't repeat. A quasi-crystal is kind of like a 3D version of that on an atomic level.
Okay, that's hard to picture, but
Right?
cool.
Yeah.
And these were found in nature before.
They were first made in labs back in the 80s, which was a huge discovery. Later, they were found naturally, but only in very specific places, mainly certain types of meteorites, so very rare.
Rare in nature, complex to make in a lab, and they found one inside Trinitite.
That's the really remarkable finding, yeah. It was reported just a few years ago in 2021. Our research team found this tiny grain, only about 10 micrometers across, really small, inside a sample of red Trinitite, and it showed this distinct quasi-crystalline structure.
How big a deal is that?
Oh, it's hugely significant. For starters, it's now the oldest human-made quasicrystal ever found.
Human-made, because it formed in the bomb blast.
Exactly. And its composition is unique, too, a mix of silicon, copper, calcium, and iron. Something new to science. But maybe the most interesting part is how it likely formed.
The extreme conditions.
Precisely. The fact that it formed under those incredibly intense, rapid, violent conditions of the nuclear explosion, and importantly, in the presence of metals like copper and iron from the device, well, that fits perfectly with how we think natural quasicrystals form in meteorites. They also seem to require violent impacts involving metals.
So an artificial, incredibly violent event mimicked the conditions of, say, an asteroid impact and created this super rare form of matter.
It certainly looks that way. It's this amazing link between extreme planetary processes and human-made events.
It really ties together the sort of cosmic scale and the terrestrial human scale of extreme events. Okay, so decades have passed. Is Trinitite now just a sort of historical oddity, a collector's item, or does it still have real scientific relevance?
Oh, it absolutely still has significant scientific value. I mean, for one thing, it's still slightly radioactive.
Right, even after all this time. Where does that radioactivity come from?
Well, the research explains it's a mix of things. There's some residual plutonium and uranium from the bomb fuel that didn't fission. Then there are the fission products, the broken bits of atoms, some of which have long half-lives, like cesium-137.
Okay.
And finally, activation products. Those are isotopes like cobalt-60, formed when neutrons from the blast slammed into stable atoms in the surrounding soil and the tower, making them radioactive.
And is that radioactivity spread evenly through the glass?
The study suggests it's often concentrated more towards the surface of the Trinitite pieces.
I know people do collect this stuff. Is it? Is it safe?
Well, collectors certainly obtain samples. One source mentions it's available from mineral dealers. But given the mild radioactivity, it's definitely something to be handled with care and respect, not something you'd make jewelry out of, for example. And scientists studying it use techniques like X-ray fluorescence, XRF analysis. That's not just for safety, but it helps them analyze the composition non-destructively and, importantly, verify if a sample is actually genuine Trinitite, not a fake.
Okay, so beyond collecting and safety, what's the ongoing scientific value? Why keep studying it?
Well, it's still a unique, frankly irreplaceable sample of material that was exposed to conditions, extreme temperature, pressure, incredibly rapid cooling that are almost impossible to replicate accurately in a lab, certainly not on that scale or complexity.
So it's like a natural experiment sample.
Kind of, yeah. Studying its detailed mineralogy, its structure, how the different elements are distributed. It provides data points for understanding material behavior under these extreme, very short-lived conditions. And like we saw with the quasi-crystal, that discovery in Trinitite has actually spurred scientists to look more closely for similar structures in other impact classes, like those from meteorite craters.
So it opens up new research directions. And I think you mentioned nuclear forensics earlier.
Yeah.
That sounds really important.
It is. This is probably one of the most critical modern applications. Trinitite and the similar glassy debris found at other nuclear test sites around the world acts as an incredible physical record of the nuclear event itself.
How can a piece of glass tell you about the bomb?
The chemistry, the structure, the specific radioactive isotopes, and where they are located within the glass. It all holds clues. As one paper nicely put it, it's like a hand sample scale history of that specific atomic blast.
So you can work backwards from the glass to figure out things about the device.
To some extent, yes. Scientists can infer details about the bomb's design, the materials used, maybe even estimate its yield more accurately. And this is where microanalysis becomes absolutely crucial.
Looking really closely again.
Exactly. Techniques like SIMS, secondary ion mass spectrometry, or electron backscatter diffraction, EBSD, or detailed XRF mapping. These let scientists analyze tiny, specific spots within the glass, not just the bulk average.
Why is that spatial information, knowing where things are, so important?
Because it preserves the original relationships between different materials from the device and the environment. For instance, one study described finding uranium and plutonium concentrated together in specific calcium-rich spots in the glass.
What did that tell them?
It provided direct evidence that the tamper material, which was likely calcium-rich, was intimately mixed with the nuclear fuel before or during the detonation. Another example, looking at the isotopes of lead.
Lead?
Yeah. By measuring the isotopic ratios of lead in different microscopic areas, they could distinguish lead that probably came from the bomb components, which has a specific isotopic signature, from the common natural lead that was already present in the desert sand.
Ah, I see.
These kinds of details are absolutely critical for nuclear attribution, figuring out the specifics of an unknown device, maybe for treaty verification or investigating illicit tests. And you completely lose that fine-grained information if you just grind up the sample and analyze the average composition.
It's just incredible that so much specific forensic data about such a complex event is locked away in the structure and chemistry of the glass it created. So let's bring it all together. Why should, someone listening care about this weird green glass from the New Mexico desert?
Well, I think because Trinitite is so much more than just, a historical souvenir. It's a truly unique artifact from one of the absolute turning points in human history.
Yeah.
It physically embodies these extreme physics, these complex geological processes happening on human timescale.
Tangible piece of history.
Exactly. And it's a piece of history that's still teaching us things. It's yielding valuable scientific insights from really fundamental material science, like discovering that quasicrystal, all the way to very practical applications in nuclear forensics, helping us understand and monitor nuclear devices through their debris.
It really hammers home how much information, how much history and science can be packed into seemingly simple materials, especially ones formed under such extraordinary conditions.
It really does. It shows how looking closely with the right tools and the right questions can reveal layers upon layers of information about how something came to be.
It definitely makes you wonder what other secrets might be hiding in plain sight, in materials all around us, just waiting for us to look closer.
A very good thought.
If you wish to hear more content like this, please subscribe to our channel. We'll keep bringing you new discoveries and fascinating stories from the world of gemstones here at GemMatrix.